In this experiment, we're going to do a lot of different types of chemical reactions, and as you do them, you're going to be looking for the evidence of a chemical reaction. For example, a color change, a change in mass, which on this one, something changes mass sometimes when a reactant or product is a gas. In this case, we'll be heating copper, and as oxygen from the air bonds to it, it should appear to gain mass. Anyway, a precipitate formed, and you know that is when you have two clear solutions and you mix them and it gets cloudy. A gas formed, of course, that looks like bubbles most of the time when you see that. Okay, so precipitate again, we've seen that before, and know that this little down arrow is sometimes used for a precipitate. Sometimes we use the state symbol, and know that these little symbols are called state symbols. Whenever you write your chemical equations in this experiment, you need to include state symbols on everything. So I'm just going to go through the different types of reactions, and on these first couple, I'm going to give you the reaction and the product. On the combination reaction, and I'm going to add some to it, notice this is not balanced, so when you write these, and I'm doing some of the work for you, you need to make sure that you balance them. And so I balanced oxygen and then copper. And then you also need to know, when you're doing the experiment, you'll see that you have solid copper, and you can guess that the oxygen it's combining with comes out of the air and it's a gas, and then you will see the solid product. So you will be able to add those state symbols to it. If it has a catalyst, be sure to include the catalyst too. The catalyst goes either under or over the arrow. Usually, well, it doesn't matter. Okay, so that is our combination reaction. Our decomposition reaction, this would be really hard to predict these products. This is kind of going to be given to you as a known, that this is how it breaks down. You're going to observe this and decide the state symbols, and you are also going to balance it. This is one of the answers you have to put on your thing. I am going to put the catalyst up here for you, just a reminder that you need to include those. So this is the reaction that we're doing. This one we perform in the hood, and we'll do a glowing splint test where you'll have a piece of wood that was on fire, but you blow it out and it just has that little glowing ember. And when you put it up to the test tube, this oxygen supports combustion, and it will make that reaction, the combustion reaction, go faster, which means that the glowing splint lights up into a flame again. But anyway, so that one we do in the hood. And again, you won't have to predict the products on a decomposition reaction like this, especially this one didn't break down to the elements. We're giving you that. On the single displacement reactions, a more active element can replace a less active one. And you do need to have an idea about how to predict products on these. Let's look at the top one. So zinc is not an ion here, it's the solid. I put a 0 up there for its oxidation state. And you'll see this is a solution. So to start predicting the products, what I do is I see the element, what type of ion does that form? And zinc forms a +2 ion. That's its common ion. And so then I can look at this compound, the ionic compound, and I know which ion it's going to replace. It's going to replace the positive one. So it'll go with the sulfate, which has a -2 charge. And I look at those charges to make sure this is a good formula, and it is. It's neutral. And then what's left? The copper. And when the copper gets replaced, it goes back to being neutral. So we'll put a 0 there on it. And I'm going to tell you, it is a solid. It's sometimes hard to observe that solid. but it is a solid there. If you let this react for a while, you will see these gold little flakes or copper colored little flakes, maybe orange, floating on the top, the surface. And if they float there and you look carefully, they're shiny orange and they're kind of cute. But anyway, so there's that reaction. It appears to be balanced. And then I said, we didn't check this. A more active element can replace a less active one. So if we go to our activity series of metals, I see that zinc is above copper. So that means it can replace copper. So that reaction could occur. So higher on the chart means more active. Sodium could replace zinc or copper. An element can replace whatever's below it. On the halogens, of course, they form negative ions, but they can be the replacing element as well. And fluorine can replace any of those below it. If you'll notice, this is their order on the periodic table. Okay. So on this next one, if you look, it's kind of the opposite of the first one. In this one, what would happen is that copper would replace zinc. But we see on here that copper is less active, so copper can't replace zinc. So we'll write no reaction. In lab, what you're going to be doing is you're going to be setting up 2 test tubes, one for each of these, and you should see one reacts and the other does not. So that goes with this. Okay, and actually double displacement. So we're going to do, this is the most common one, double displacement, or you could say replacement. You have 2 ionic compounds and they kind of switch positive to negative. So in other words, the positive part of one goes with the negative part of the other, and you need to be able to predict these products. So what I do is I start by putting charges up here. On an acid, these hydrogens in front pretend like they're hydrogen ions with a +1 charge. Sulfate is -2, barium forms a +2 charge, nitrate is -1. So you need to know your polyatomic ions and charges. And so I can see that hydrogen, positive part of one, so it's like the front part of one goes with the back part of the other. So hydrogen will go with nitrate, and I put the charges there so I can check and make sure this is a valid formula, and it is. If it's not, I would add some subscripts and fix it. But anyway, it's good. And then I can see that my barium will go with my sulfate. And that is a good formula. Positive one always first, then negative one. Then we might want to balance this. When you balance a double replacement reaction, you can treat the polyatomic ions as a group. So I don't have to balance oxygen. That would be a nightmare. Separately, or nitrogen separately. I can just balance nitrates, sulfates, hydrogens, and bariums. Now this is a reaction that you do in the lab, and when you do this, you mix these 2 solutions, which are clear, and it does turn cloudy. And since it turns cloudy, you know that one of these is insoluble, or in other words, is a precipitate. And you have to know which one. Well, I can tell right away, HNO3 is a strong acid. It wouldn't be a precipitate, but also I see it contains nitrate, which nitrate doesn't form any precipitates. So this one must be our solid or precipitate, and this one is aqueous. It's a strong acid. Okay. And then we're going to do a few more of these, but you need to know your solubility rules, and these are the ones that you need to know for lab. Your experiment today involves group 2 ions, like magnesium and barium and calcium and those in the second column of the periodic table, they form less soluble compounds or fewer soluble compounds as you move down the periodic table. In other words, barium is the lowest one that you will use, and you'll see that it forms a lot of precipitates. And magnesium at the top, you'll see you don't get very many at all, or if at all. The group 1 cations, that's the first column of the periodic table, like lithium, and then on down. In this experiment, there's a polyatomic ion we don't always have you memorize, but you need to know that this ion is oxalate. Okay, let's predict some more products, more chemical equations. Let's look at what happens with this one. So I start by putting my charges on here, and then I figure out what goes with what. So the front part of one goes with the back part of the other. Look at the charges, that's a good formula. Then I do my other one. The front part goes with the back part. But if you do this reaction, you'll find that there is no precipitate. It does not get cloudy. And so let's see why. Well, both sodium and nitrate are never in precipitates. They're always soluble. Same thing with potassium. So instead of writing these products, that's incorrect. If there's no precipitate, we're going to write no reaction. And actually, I'll show you, let's look at the picture of what's happening. So when we put these in this solution, the sodium and the chloride are actually separate, right? Because it's an ionic compound that's soluble in water. So that will be ionized. Same with this, it'll be ionized. So we basically start with 4 different ions that are separate. And so that's this situation. We have 4 different ions and nobody's getting together. So that's no reaction. This is a case where you put 4 together and then 2 of them find each other and form a precipitate, and that's why you have a chemical reaction. So on this one, no precipitate means no reaction. Let's write products on this one. And let's just say it was given, but maybe you perform the reaction and you see that there is a precipitate, then you can write what the products are. So magnesium would go with carbonate. Okay, and that's a good formula. Point out something important. I did not keep this 2. And the reason that I did not is that 2 is there because of this plus 2. So I don't bring it over. It's not needed here because I have a plus 1 there. And yet, I did keep this 3. This 3 is there because it's part of the polyatomic ion. So you keep the subscripts that have to do with the polyatomic ion that are part of that, but you don't keep subscripts that were present, like this one. It's there because of the -2, and I don't need it here. Okay, so keep track of which ones you need to do. Let's balance real quick. Is it balanced? No. So on these, balanced by polyatomic ion, 2 nitrates, 2 sodiums, 1 carbonate, 1 magnesium, 1 magnesium. So I just go in that in an order. I see something that's not balanced and then just do kind of a chain of checking. Okay, then I need to know which one is the precipitate. Well, what I know is that both sodium and nitrate can never be the precipitate. This will always be aqueous, and so this must be the precipitate because I was given that one forms.